Next up is question 1 on the worksheet. It says to find and analyze the critical points of each function. And for part A, we're looking at the function f of xy is equal to x squared minus 2x plus y squared minus 4y plus 5. As outlined in the last video, our first step is to find the critical points. So we're going to start by taking the partial derivatives of f with respect to x and y, shown here. And then what we're going to do is set these equal to 0 and solve for x and y. So if I set the x derivative of f equal to 0, I see that x is equal to 1. If I set the y derivative of f equal to 0, I see that y is equal to 2. So in other words, the point 1, 2 is a critical point of f. Alright, so now let's go ahead and classify this critical point. We can do that using the second derivative test. Alright, so we're going to compute the xx, the yy, and the xy derivatives of f. Those are shown here, so 2, 2, and 0. Go ahead and compute our quantity d that we defined in the last video. So this is the product of the xx and the yy derivatives minus the square of the xy derivative of f. So in this case, this is going to be 2 times 2 minus 0 squared, and that's equal to 4. And so now, in particular, since d here is a constant, it's just 4, d evaluated at 1, 2 is 4, and d here is positive. Note also that the xx derivative of f at 1, 2, well, it's just 2. That's positive, telling us that the concavity of our surface in the x direction is positive. So from our result in the last video on the second derivative test, we are at a local minimum. Okay, so one note here. Note that we can go ahead and complete the square and rewrite this expression for f of xy as quantity x minus 1 squared plus y minus 2 squared. This is just a paraboloid, okay? It's the paraboloid x squared plus y squared, and we've just shifted it 1 unit in the positive x direction and 2 units in the positive y direction. So it's a paraboloid with vertex at the point 1, 2, 0, hence our result, right, saying that we have a local minimum at the point 1, 2. In fact, this is a local and an absolute minimum, right? That's the point on our surface where the z-coordinate is as small as possible. All right, so that is part A. Let's check out part B. Okay, so here we have the function g of xy is 4 minus the square root of x squared plus y squared. So again, we'll go ahead and identify the critical points. So we find these partial derivatives, the x derivative and the y derivatives of g. Those are here. Okay, and now notice that if I set these equal to 0, okay, well, here, if this fraction is 0, then the numerator must be 0, saying x is 0. And if this fraction were 0, then y would have to be 0. However, right, if both x and y are 0, okay, these partial derivatives, in fact, are not defined because I'd be dividing by 0, right, because of that x squared plus y squared under the root in the denominator of both of these expressions. So while 0, 0 is in the domain of our function g, these partial derivatives are not defined, and so 0, 0 is a critical point of g. All right, so now let's go ahead and classify the critical point. Now, since these partial derivatives are not defined, the second derivative test that we introduced in the last video does not apply, right? The second derivative test only applies if both of these partial derivatives is 0 at our critical point. So what do we do in this case? Well, we're going to have to look at the graph of our surface. Now, if I look at just the equation z is equal to the square root of x squared plus y squared, the graph of this equation is a right circular cone, okay? Now, if I look at 4 minus the square root, well, the negative in front of the square root is just going to flip the cone upside down, and this 4 is just going to shift the cone 4 units up along the positive z-axis. So we're going to get this cone here. Now notice when x and y are both 0, we're right here at this peak, 0, 0, 4. So I can see just from the graph that at this critical point we are at a local, which also in this case happens to be an absolute maximum. Okay, very nice. And now for part C. Here we have h of xy is x squared minus y squared. So again, we can start by looking at the critical points. So the x derivative is 2x, the y derivative is negative 2y. We can set those to 0. And here we find that x and y both have to be 0. So that's our critical point. And now let's go ahead and classify. And since both of these derivatives are 0 at our critical point, we can apply the second derivative test. So here's the xx, the yy, and the xy derivatives. And our quantity d then turns out to be 2 times negative 2 minus 0 squared. So that's negative 4. Again, d is constant. In particular, d evaluated at the origin is a negative number, right? It's negative 4. So from our second derivative test, we know that h has a saddle point at the origin. Okay, so now, real quick, just to bring up a picture of the graph of this surface, we can see here for z equals x squared minus y squared, we're looking at this surface that looks like a Pringle chip, or in other words, it looks like a horse saddle. So at the origin, we can see, right, we're at neither a max or a min, right? If I move like this, right, along this contour, right, along the x-axis, my z-coordinate will increase. But however, if I move along this contour, right, along the y-axis, then my z-coordinate is going to decrease. So I'm not at a max or a min, I'm at a saddle point. All right, well that does it for this problem. I'll see you in the next video.